So let's come back to those reasons for using the MANOVA now that we're done with replacing repeated measures design. The next one is a reduction of experimental wise type 1 error compared to ANOVA for multiple DVs. So generally speaking, if you have more than one DV in a design where you have multiple IVs and multiple DVs, more often than not, the answer is going to be to run a MANOVA. And specifically for reason number 2, and that is that it would be inappropriate to run multiple ANOVAs because each ANOVA is going to be, again, a unique estimate of the overall chance of error. But if you're running multiple ANOVAs, then the chance of there being error in any of them is increased beyond what your p-values are showing. Now, there are going to be some times where you can make an argument for doing this still to simply run additional MANOVAs, and usually that argument is going to come from strong, basically theoretical or literature review-driven reasons, basically suggesting that though you are looking at 3 different DVs, you're not expecting them to be related, you're expecting them to be fairly unique in their relationships, and at that point you could make that argument. But more often than not, your standard kind of best practices are, if you have multiple DVs and you have categorical IVs and those DVs are continuous, you should be using a MANOVA. And the other reason to use a MANOVA is, as I was talking about, there are situations where it actually provides more power. And I'm going to talk about some of those in the examples that are coming up, specifically kind of illustrating how it actually increases power beyond what I was just talking about verbally earlier in the previous lecture. And again, I'm going to talk a little bit about how if those IVs are negatively correlated, that can sometimes help, but it can also actually end up creating a problem, which could result in you making the argument again for separate ANOVAs, and we'll discuss that as well. So again, when we're looking at MANOVA and power, if I have a DV and I'm looking at the mean difference, so we'll look at DV1. At the bottom of DV1 is basically comparing the difference between my 2 groups. So I have a dependent variable, it's got divided by 2 categories, so I'm looking at the mean difference of category 1 and category 2 represented by those normal distribution curves. And if you look at that, you'll notice that though there are some differences, there's a whole lot of similarity. When I'm looking at the dependent variable 2 along the side, again, I'm dividing out that continuous variable by my 2 categories, my IV. And again, there's some differences, but there's also a lot of similarity. When I look at it from a MANOVA, though, if I'm looking at both of those DVs on that IV, I'm actually looking at how, again, they form centroids away from each other. So in this example, there's a lot of similarity between the outcome and the 2 levels of my IV on DV2. There's a lot of similarity, in other words, not difference, but overlap in my first DV between my 2 categories. But when I look at a MANOVA, there's actually not a whole lot of similarity between the relationship between my IV, the DV, and the DVs to each other. In other words, they cluster more clearly when they're in a single analysis. And this is an example of how MANOVA can actually increase power. Now, again, if we continue to look at this situation, we can also ask what happens if those differences actually become greater. And what we're going to find is that, again, the further the difference is, individually, that's increasing power. So with DV1 and DV2, in both cases, as I increase the difference, as the effect size is greater, there's less overlap. But again, at the multivariate level, the MANOVA, that difference is becoming even clearer and even stronger in this situation. And again, we see that as we look at the amount of similarity versus the amount of difference. Now, we're also going to talk about what happens if they're negatively correlated. So as the differences are, in other words, group 1 is stronger or higher on DV1, but group 1 is actually lower on DV2. So in this case, if those negative correlations occur, what often will happen is that we may find if there's a non-significant difference in DV2 and there's a negative correlation, and this happens a lot also even if they're positively correlated. If we change the situation to where the differences between the DVs is one of the DVs has very little change and the other one has a larger change, we may actually find out that the MANOVA is less powerful. So in this case, if we looked at DV2, we would find most likely non-significant. If we looked at DV1 individually, we'd probably find it is significant. When we put them together, we find overall they're not significant. So also recognize that MANOVA can, in some situations, be less powerful. And this might be an example where you could use past research and theory to suggest, though I'm measuring DV2, I'm actually not expecting it to have a strong relationship, but I want to make sure that I test for that relationship. But I am expecting a strong relationship with DV1, and because of that combination, I'm going to actually run two separate ANOVAs instead of a MANOVA, because the MANOVA very well may become basically too much variance is going to DV2 to really find a relationship in DV1. Now, if we continue that negative relationship to where basically, again, in DV2, we had one condition much lower, and in the DV1, that condition is much higher, we'd actually find, again, kind of the flip side. We'd start to see more power again with the MANOVA. And again, this is just kind of illustrating how MANOVA can also be less powerful. And though it is our go-to, if you will, when we have multiple DVs, it's not a bad idea to also think about what are our hypothesized expectations for those DVs. Generally, we're not going to include a DV that we're not expecting to find a difference on, but if that for some reason is, or a small difference, you may have one of those situations where you could make a theoretical argument for running separate ANOVAs. Okay, so let's just walk through the MANOVA procedure, and really, like I said, there's not a whole lot more going on here than what we've already been covering with ANOVA. We're just adding, again, another layer of the onion. So we're going to run a MANOVA to look for the effects of all DVs and all IVs at once. In other words, again, it's an omnibus test, and if significant, it says keep digging. So again, if the MANOVA is significant, we're going to examine the individual ANOVAs for each DV. So all a MANOVA says is it's okay to look at individual ANOVAs. So basically, another way to think about it is that if you don't have a good theoretical reason to say I should be looking at individual ANOVAs, the MANOVA gives us that license. It is that one omnibus p-value test. Is there significant patterns in this total data set? And if so, now I can go searching for those differences, knowing that my overall chance of being wrong due to chance, my p-value, has been obtained through that multivariate test that looked at all differences. If each ANOVA is significant for a DV, then again we have to go down the layers of the onions. We run the post hoc tests, we look for planned comparisons, or in the case of interactions we use simple main effects. We basically treat each DV as if we were running that ANOVA, which in fact we are. So again, we're going to look at the SPSS for the omnibus test of the actual MANOVA. We're going to report the MANOVA's Wilk lambda, and we're going to talk a little bit about what SPSS gives us and why specifically we usually report Wilk's lambda. And then we're going to report the omnibus ANOVA F test for each DV. At that point, we're then going to, again through SPSS, do the additional tests. We're going to report the post hoc tests, any planned comparisons, and any simple main effect tests. So at the between subjects ANOVA, we're doing a multivariate F ratio. In ANOVA, the variance in the F ratios are estimated by dividing the sums of squares by the degrees of freedom, so very similar to an ANOVA. And in MANOVA, the sums of squares of the cross-product matrices are then divided by the determinant matrices. So this is basically matrix algebra. Again, I don't want to make too much of this, but when I was learning this stuff, I had to learn how to do matrix algebra, and I had to conduct MANOVAs by hand. I'm not going to make you do that. I don't think it's very practical. And honestly, I'm not sure it really gave me an understanding, because I basically was just learning how to do the formula. It was hard for me to really understand even what's happening, which makes a fair amount of sense. It's a fairly complex thing that we're doing, but at the end of the day, it is still doing the same thing as any other F ratio. We have the total of effects on the top of the equation and the total of the variance on the bottom. It's simply that now, because we're looking for multivariate centroids, finding those effect sizes and calculating them are much more difficult, and the total variance is also more difficult to calculate. Once we have that F ratio, we're simply wanting to find out, again, is it significant? And normally what we're going to report is Wilk's lambda. It ranges from 0 to 1. And again, it is considered, it's an F ratio, but to make it distinguished from an ANOVA, especially because if we have a significant MANOVA, we are going to then conduct F tests, specific ANOVAs on each individual DV. We want to distinguish the overall omnibus test, and that's usually going to be Wilk's lambda. If you're wanting to be extremely robust in your willingness to reject anything but clearly highly likely effect sizes, you could use Philly's trace. It's more robust to heterogeneous variances. It generally gives you a little bit better of a read if you've got a lot of variance in your DVs, a lot of near violations of assumption. So it's a more rigorous test. There's Hotelling's T or Trace T. It's a multivariate T-test. So basically, if you've got a bunch of DVs, but your IV is just 2 levels, you shouldn't run a bunch of T-tests. You can run the Hotelling's T. It is basically a multivariate T-test using just one IV with 2 levels. So if that's the situation you're in, don't report Wilks Lambda, report the test that's specifically designed for that situation, Hotelling's T. And finally, there's Roy's largest root. It's unpredictable. In some unique but rare cases, it works well. So again, Roy's largest root is almost always going to find some differences. So it's not very robust. It tends to underestimate or overestimate effect sizes. It tends to give us p-values that are not quite trustable. The situation where you'd use Roy's largest root is usually when you're kind of coming from the bottom up. You know there's some pretty big differences that you're wanting to talk about. They're the ones you hypothesized, but there was enough noise in the data that the F-test from Wilks Lambda actually said not significant. So this would be a case where you're actually doing what's right. You're using a MANOVA because you have a lot of variables in play, but your hypotheses are really just focused on a couple of key differences. In that case, you may actually want to use Roy's largest root, but again, recognize you're going to have to defend theoretically why you use that particular test of the MANOVA. So there are 2 stages in examining whether or not a relationship exists with predictors and outcomes. There's the omnibus F-test, an overall test that determines if any of the outcome variables are related to the predictor variable. And again, that's what we're calculating with MANOVA. And then the next layer of the onion, the univariate follow-up ANOVAs. So the multivariate test is already controlled for type 1 error rate. So the univariate tests now indicate which outcome variables, which DVs, were actually significant. Now, the univariate tests are still subject to alpha inflation, so there's still a bit of an argument, especially if you have a lot of DVs, that you may be running into a situation that even with the omnibus F-test, that it may not be appropriate to not adjust your p-values. Remember, there's the Bonferroni adjustment we often use in t-tests, where if we're running multiple t-tests, we actually reduce the p or the alpha that we're willing to accept for significance. Some people, Huberty in 1989, for example, suggested that with 3 or more DVs, that may also still be worth doing. So let's talk about some of the weird situations. Why might I get a significant univariate test but not a significant multivariate test? So it's hard not to look down the SPSS rating. So for example, you may find that your MANOVA is non-significant, but you can't help but glance down at those univariate ANOVAs and all of them are significant. So the first thing to recognize is univariate tests may not control for alpha inflation. So even though they're significant at, say, for example, 0.02, 0.03, 0.04, in reality, according to the multivariate test, that was actually, each one of them was 0.06, 0.07, 0.08. Multivariate test examines the correlations between the dependent variables, and once these relationships are considered, the power of tests may be affected. So example, we may also get a situation where, again, the MANOVA doesn't find a difference, or we might find the reverse of that, where we actually find the MANOVA found a difference and none of the univariate tests claim there's a difference. So just remember that they are testing for different things, and there are going to be some times where you get some pretty unique situations. So again, instead of examining mean difference for a single outcome, the multivariate test is examining multidimensional mean differences. As the centroid is multidimensional, it also is an aggregate of weighted means across those IVs. So all of this is basically to say that you will occasionally find a situation where the MANOVA is significant and you do not have any significant ANOVAs. In that case, you usually can use a less robust test of ANOVA. And you can have a situation where the MANOVA is not significant, but the univariate tests are. And again, that might be a situation where you can come in and make an argument, for example, of using Roy's largest root as your actual statistic for the MANOVA, if you can defend that with theory. So you can also use MANOVA with the within subjects, and again, most of the procedures can be directly applied to with the within subject analysis we talked about with ANOVA. It basically combines the tools of MANOVA with the within subjects ANOVA. However, when possible, you may want to look at a different statistical technique called profile analysis. Profile analysis, however, can only be used when the same scale is used for each dependent variable. So if you are going to be in a situation where you're doing a within subject design and you're thinking about using MANOVA, the first question you should ask is, can I get my dependent variables all on the same scale? So for example, if I was going to use grade, GPA, grade on statistics, grade on psychopathology, and grade on vocational psych exams, those might all be on different metrics, but if I could actually change them all into percentages, I could then do a profile analysis. I could look at verbal and quantitative GRE scores because they are on the same scale. I could compare 3 different tests if they were all on a 1 to 100 scale. So if you can take those DVs and get them all into the same scale, you can use a profile analysis, which actually is a more powerful technique to look for within subject differences with multiple IVs and multiple DVs. If you can't, then a within subjects of MANOVA is appropriate. Because what a profile analysis lets us do is not just look for the mean differences at each time between each DV and with each predictor, we're also able to look for actual profiles or patterns within that data, which again allows us to be, because we're not just looking for mean differences, we're not just looking at the IV's effect on the DVs, we're also looking for consistent patterns across DVs. It can be a more powerful design. And finally, we have MANCOVA over MANOVA. So again, MANCOVA simply is, on top of everything else, adding one more layer of a confound or an extraneous variable that we're wanting to account for and remove before we actually do the rest of the analysis. So again, covariates can be continuous or categorical. Again, categorical being dichotomous. Covariate is used to account for variation. It contributes to the dependent variables and remove before we run the additional analysis. And including a covariate in the model can reduce or increase the F ratio. It depends. So the more the covariate is related to the IVs, you're probably going to lose power. The more it's related to just the DVs, the more likely you are to increase power. Just again, think of those Venn diagrams. If the covariate is eating up variance explained by the IVs, you're losing power. If that covariate is explaining variance that was unexplained in the DV, that means the ratio between how much your IVs are explaining the DV are going to get larger. It's going to get stronger. Again, we have to check the assumptions because once we put in a covariate, the assumption is that that covariate has a linear relationship with any continuous DVs.